Welcome back, everyone. Today, we're diving into the fascinating world of quantum materials and the mind-bending concept of coexisting phases. You might be thinking, what's a coexisting phase? Well, get ready to have your mind blown. Imagine a glass of ice water. It's not just a simple drink, it's a perfect example of two phases existing simultaneously. Water can be both a liquid and a solid at the same time. Now, fast forward to the quantum realm, and things get even more intriguing. In this video, we'll explore how physicists are witnessing the assembly and reassembly of electrons in a material, creating these mind-bending coexisting phases. So, grab your thinking caps, and let's dive in. First, let's talk about the star of our show, erbium tritelluride. This rare earth material is like a quantum playground, allowing scientists to study the behavior of electrons in a way that's both fascinating and complex. When cooled to extremely low temperatures, something magical happens. The electrons start to organize into a wave-like pattern, known as a charge density wave, CDW, phase. But here's the twist. As we continue to cool it down, a second wave pattern emerges, creating a checkerboard of coexisting electron phases. It's like a quantum version of a game of chess. Now, here's where things get even more intriguing. The first phase, the dominant one, forms gradually, just like how liquid water transitions into vapor. But the second phase, the subdominant one, takes a completely different route. Instead of a smooth transition, it forms in isolated pockets that eventually expand, similar to how liquid water crystallizes into ice. This unexpected behavior has been a topic of debate among physicists for a while, and our study provides a powerful new way to uncover the hidden physics behind these phase transitions. To understand this better, let's break down what a charge density wave is. It's essentially a pattern of electrons that organize themselves into a wave-like structure. The crests of the wave have the highest density of electrons, while the troughs have the lowest. In some materials, this strange coordinated behavior occurs at supercold temperatures, and it's not just limited to erbium tritelluride. Scientists have observed these waves for decades, and they've been linked to various forms of magnetism and superconductivity. Now, here's the million-dollar question. Why do some materials host multiple phases while others don't? And when multiple phases do exist, how do they interact? Do they reinforce each other, compete, or coexist independently? This is where our study comes in. We wanted to get a clear view of these charge density waves in a material that hosts two CDW phases simultaneously. By doing so, we could shed light on how superconductivity and other complex phase transitions occur. To study this, we used erbium tritelluride, which can be synthesized in the lab in atomically thin sheets. We cooled the samples to extremely low temperatures and then used a clever technique involving laser pulses to shake and listen to the system. By doing so, we could observe how the electronic phases recovered after being disturbed. What we found was fascinating. The first phase re-emerged gradually and uniformly, no matter how hard we kicked the material. But the second phase took a different route, forming in isolated pockets that spread, similar to ice crystals. This rare, first-order transition was not expected, and it provided valuable insights into the long-debated mechanism underlying the emergence of the subdominant CDW phase. As we continue to explore these quantum materials, we might uncover more complex interactions between different phases, which could have significant implications for high-performance quantum devices. So, stay tuned, as the world of quantum physics never ceases to amaze. In conclusion, this study showcases the incredible complexity and beauty of quantum materials. By witnessing the assembly and reassembly of electrons, we gain a deeper understanding of how these coexisting phases emerge and interact. It's a fascinating journey into the heart of quantum physics, and I can't wait to see what other surprises await us in this exciting field. Thanks for joining me, And don't forget to like and subscribe for more mind-blowing content.